The seed for large language models started from encoder-decoder architecture, which initially uses recurrent neural network called RNN. RNN is connected recursively, which means one cell is connected to another cell sequentially. The encoder-decoder RNN model has two parts: the encoder, which reads the input sequence and compresses it into a hidden state, summarizing the input, and the decoder, which generates the output sequence step by step. We can discuss how RNN evolved in terms of the cell internal design. Then we will discuss how recurrent neural network used semantics to solve some of the natural language processing projects. Then we move to how the encoder decoder model evolved into a transformer architecture and how the transformer architecture is used in the contextual embedding for semantic similarity in NLP or natural language processing. Please watch until the end of this video for more clarity on these issues. RNNs are basic recurrent neural networks that process sequences step by step, but it struggles with long-term dependencies due to vanishing and exploding gradients. It means either derivative is 0 or infinite while learning parameters due to simple cell structure. LSTMs improves on RNNs by using input forget and output gates, which help retain important information over long sequences and overcomes vanishing gradient issues. GRUs are simplified LSTMs with update and reset gates, which offers similar long-term memory capabilities with fewer parameters, and hence it is faster training model. Bidirectional RNNs read sequences both forward and backward directions, capturing context from past and future tokens. It uses either LSTM or GRU to handle gradient problems. Neural tuning machines called NTM combines RNNs with external memory, enabling algorithmic reasoning and complex pattern storage while internally relying on LSTM or GRU. It is very complex and hard to train. We will discuss now how we can use semantic word embedding and recurrent neural network in sentiment analysis. Please subscribe, like, and comment for more videos. In sentiment analysis, input text sequence can be represented with a semantic word embedding layer. It is used to convert words into dense vector representations that captures their meanings and relationships. These embeddings are then fed into LSTM layers, which process the sequence of word vectors and capture the contextual information and dependencies between words across the sentences. This means it understands negative phrases, positive phrases, and neutral phrases very well. By combining embeddings with LSTMs, the model can leverage semantic meaning and sequential context, making it much more accurate than traditional bag of word approaches. Then it uses fully connected layer to find distinct patterns across sentences, followed by classification layer called softmax layer. This architecture is particularly effective for handling long sentences, negations, and subtle difference in sentiments in text data. Overall, the embedding layer captures word-level semantics and the LSTM layer captures sentence-level context to predict sentiments. You can also apply this architecture for language translation and text generation, but you need a similar decoder architecture for these two types of problems. RNN captured context via long-term or short-term memories. None of the RNN-based encoder-decoder models do not provide attention to some phrases in encoder to generate phrases in decoder. The attentions are important especially for translation and question answering related problems. The LSTM cell design is not capable to address those problems. In next phase, LSTM models have enhanced with the different attention mechanisms to focus on important parts of input sequence. One is global attention, considers all encoder states have same attention to each output state, providing full context, but it is computationally heavy. Low-Yang attention uses a dot product on encoder states for efficiency, though it may miss subtle relationships. Self-attention captures internal dependencies within the input, while hierarchical attention focuses on word and sentence at multiple levels. And temporal and local attentions concentrates on nearby context to reduce computation. Each mechanism improves LSTM performance for tasks like sentiment analysis or translation, but comes with the trade-offs in complexity, memory, and the range of context captured. Main bottleneck in the entire architecture is sequence in nature. There are five components in transformer architecture. These five components enriches drawbacks of recurrent neural network attention mechanisms and understands the complexities in natural language processing. Positional encoding understands the relative or absolute positions of words in the sequence. It uses sine and cosine functions of different frequencies. No recurrent neural network is used to identify words in the sequence. Scale dot product attention is used, which is also called a self attention, to compute how strongly each word should attend to every other word. Multi-head attention is used to run multiple scale dot product attention operations in parallel, allowing the model to focus on different types of relationships. Feed-forward networks performs transforming higher dimensions and applying activation function to learn better relationship at each position of words in sequence. Layer normalization is used to avoid vanishing or exploding gradients. Let us dive deep into self attention or scale dot product attention. It operates on three inputs: one is query, two is keys, and three is values. Think of searching a file in a file cabinet. First, you have a query, what file you want to search. Then, your query is compared against a set of keys. In this case, the set of keys are the titles, tags, and descriptions of the files within the filing cabinet. After this, you will find the file that best matches with your query. The filtered file from that file cabinet is called a value. This is exactly scale dot product attention understands words that relates to each other in a sequence. Let us discuss about multi-head attention. The multi-head attention operates parallelly across all words within a sequence to understand different relations that exist between words, which has ability to understand like human. Here you can see the word it has referred to animal, which is called entity resolution, and there is a adjective relationship also. You can use two scaled dot product to solve these two issues. This is called multi-head attention. Finally, you can see encoder and decoder architecture in transformer model. Encoder and decoder contains all five components that we have discussed. You can also see an additional softmax layer at decoder side to generate words and their probabilities. This architecture has ability to understand hard problems in natural language processing by combining all five components in both encoder and decoder. This has ability to parallelize operations for fast training. This architecture also has ability to understand like human, which outperforms all RNN attention mechanisms. Conclusions and key takeaways are here. Various RNN architectures that they have evolved over cell structure and attention mechanisms are discussed. Components of transformers and their abilities to solve complex NLP problems are discussed. The components usage in encoder and decoder in transformers are learnt. Please subscribe and comment for more technical videos.